Alright, another DraftScience video presentation. Different camera. Anyway, I have to figure out where you are. Sort of. So, just going to go over some basic stuff about energy. Try to be more explicit about how things work and the common mistakes that I too have made in the past. So let's say the rocket example. This is a common one where people get a little bit confused about the idea that the rocket has to push against something, right? Or it can't take off. You know, that the exhaust doesn't work unless it's pushing against something. Well, it actually is pushing against something. That's the catch. So it's a right intuition to say that you need to push against something. But the idea is the push is happening back here. Okay, so as I explained in a previous video, the pressurized tank is basically energy going in all directions. And theoretically, when you open the tank to allow some of the fuel out, the hydrogen or the oxygen, you're changing it, you're creating a huge pressure differential, which means basically that more stuff is still hitting this wall and less stuff is hitting the surface on the opposite side because you're letting it out. So you're just letting stuff out that's going one way. And so that's one form of the energy. And then the second thing you're doing is you're taking the oxygen and the hydrogen, and by making them into water molecules, which are big, okay, you're taking the size that was taken up, the space that was taken up by the molecules, and you're increasing it, you know, I don't know, 1,000% or something. So the space they were taking up is now expanding huge. So it's like a little explosion. So you have to think about when you combine certain chemistry, you're taking chemistry that took up this much space and you're making a new piece of chemistry that takes up this much space. So it's essentially an explosion of the chemistry. You're creating a little bang, okay, that's creating pressure. Now it's always pressure in both directions. So I can't say it's a rule for every single example, but let's just say it is. Okay, we'll see if we can find examples where it's only in one direction. So in the famous half, mv squared, the half is essentially pointing out that when you explode something, when you expand things into pressure, when you create pressure, you're essentially creating it in both directions. So when you're measuring it, you know, you have your ruler. You can only put your ruler usually on one side of the thing at a time. You can only measure, you can only have a spring over here. You know, you're only measuring half of the effect, not the entire effect. I'll be back. Alright, should be back. Interruptions and such. So where was I? Alright, so in a sense, if they're all explosions and it's, you know, their explosions are happening in both directions. So it's like you're folding an elbow, you know, and you're expanding something. So you're moving the elbow this way and this way. Well, the truth is you're putting pressure both directions. You know, when you're pushing something away, it's pushing in both directions. And so really you're only getting half the energy anytime. But really that just couldn't make any difference to following the energy, because in a sense you're always just concerned about the energy in one direction usually anyway. So it doesn't change the fact that when you're measuring direction in one direction, you don't bother saying it's a half or something. It's just not very useful. But you already know that, sort of. It's already built in. Alright, so anyway, back to the story. So yeah, this is essentially always pushing. Okay, when something expands, it means everything else has to get pressurized. So it means you're making pressure everywhere around wherever it's expanding. And that's why rocket engines work, is first you have just the pressure of the escaping gases or liquids, the expansion from being a liquid to being a gas, the velocity of the molecules from that, and then you have the velocity created by the fact that you're doing this chemistry thing that makes them really big, and you're doing that inside the little coney part, and the coney is basically getting pressure in all these directions, and it's just basically converting that pressure into this pressure. That's why the cone is sort of shaped that way. And so you're gaining the energy by, you know, creating lots of expansions. So expansion, expansion, and expansion. 3 levels of expansion creates a lot of pressure, and that's what's moving the spaceship. So it is pushing against matter. it's ejecting matter. So the faster the velocity of the particles, okay, and so it's just a question of how much velocity and how much mass. So how many particles did you let loose? And in the end, how fast are they moving? Obviously, you start with lots of little hydrogen and oxygens, and you end up with a bunch of bigger molecules. So you have heavier, fewer and heavier. You're combining the little ones to make a big one, and the big one is heavier, has more mass in it, because it has lots of little ones in it, and you're making them go very fast. And by making them go very fast, it's just the MV thing. You multiply the two things times each other, the velocity and the mass, and it tells you how much energy you're throwing that way, which means you're getting the opposite pressure in the opposite direction. It's telling you how much the explosion created this way, how much stuff went this way from the explosion, the expansions, and the rest of the pressure is going in the opposite direction, pushing the ship. And the simple truth is, you don't need this stuff that's pressurized to hit anything, because it was part of you and you've ejected it. So you've already pushed against it. It's moving really fast because you pushed against it. So you've already done the idea of having something to push against. You pushed against it, it's obviously moving really fast because you pushed against it. So you've given it the energy and you're getting the other side of it. Alright, so that's one piece of interesting data. Alright, then the rest of it is the, how to, you can understand that the energy is in forms that, can excrete or not excrete. So say you're sitting in space. Now the idea what somebody would say is, okay, you don't have any pressure in space, but that's not true. Okay, so the fact is you're evading material pressure. That is, you don't have a bunch of atoms banging into you, right? There's not a bunch of big atoms touching your surface and getting, stealing your energy, bouncing into you and bouncing back off, taking energy away. Say if you're hotter than the environment, then you're going to eject the pieces that hit you with more velocity. You're going to get more because you're going to be going out more than you're going in, so to speak. The only way you go in, so to speak, the only way your atoms get pushed back in is that something has to essentially hit them. So that's the idea, is that they come in and they leave with more energy, and the more energy comes from the fact that you were pushing out more, your atoms were pushing out more than they were pushing in out with more velocity than pushing in. So you're losing some of your velocity of your atoms because you're banging into other atoms. So that's what's happening on Earth. Okay, so you get into space and that process doesn't happen anymore. So you can't lose any of your heat or your energy to the thermal, I don't even know what we call that, thermal something or other, right? It's probably an appropriate word for when it's atoms banging against atoms. But the truth is your heat's still getting out, but it's getting out in the higher forms of radiation, in terms of you're essentially vibrating. Your atoms are banging in and out at frequencies, at speeds, and the fact is it's making radio waves, and it's making some of those radio waves are called infrared light. And they're basically microwaves. You can call them lots of things, right? I mean, infrared is just another version of a microwave. It's just a high-end microwave, you could say, or you could just think of it low-end visible light. So it's all in the same spectrum. So you're really excreting, okay, in the sense that you're obviously doing something. Now, if you think there's an ether, okay, you can do that. But the truth is what there is a bunch of radiation, okay? There's a bunch of radio waves, there's a bunch of visible light, there's a bunch of microwaves, there's a bunch of stuff already coming at you, okay? And it has a certain mean frequency, you could say. It just like the environment has a temperature. And so the universe is hitting you constantly with stuff that you can't see. It's not that it doesn't. So it does. It's not like it doesn't exist. So we know the atoms aren't there in empty space, right? But it's not really a vacuum because you're constantly getting hit by a bunch of stuff. So there's a bunch of stuff coming in, and you're doing the same thing. Your bits are trying to get out, so to speak. I mean, your bits are pushing back out, and the space's radiation is what's pushing them back in. So they just keep going out. I mean, your bits, these atoms that are jiggling, they kind of want to go, but they can't go because they're always getting pushed back in because there's more energy on the outside of the universe than there is inside of you. So in spite of the fact that you think you're full of energy, you're cold compared to the actual universe. So the universe is what's really holding you together. The empty space is really what's holding you together. I mean, yes, we think the air pressure is doing it, but if you take away the air pressure, you don't explode. Okay, you expand a little bit, this and that happens, certain things happen because of internal pressures and little pops that happen, little vessels will pop, little cells will pop, different things will pop, but they're not going to explode. It's not going to be a huge increase like a rocket engine or something. And it's because space is already containing you. Space is providing the pressure. And so you are making transfers with space essentially. So that's what the infrared profile is. So in space you can look at you and you have an infrared profile. But the fact is you're going to look a lot colder than the space itself because you have a lower temperature than space has. And so you're going to radiate a frequency that's going to be different, but it's not as easy for you to get rid of your temperature until you get hotter, okay, than the environmental space. So if the light hits you and it heats you up, then you're going to heat up and you're going to radiate light, this infrared light, because you got more of it than space has. And then you're going to get back to the temperature of the space, which is this really kind of cold temperature. Relatively speaking, it's cold, but it's still hot. Sunspots, right? There's spots on the sun. It doesn't mean there's cold spots on the sun. It just means that they're a little bit cooler than the other part that's really, really hot. It's just hot. It's not really, really hot. So I don't know how to say. I mean, to say that minus 300 degrees is still hot, yeah, that doesn't sound right, but it still is compared to real zero. All right. So anyway, you're still making the transfers, and what you're really doing is your atoms are hitting into the bits that are coming in and doing the same exchanging thing in the sense that you're basically interrupting their voyage in a way. Okay, they're going somewhere and they're going to bang into your atoms and your atoms are changing the speed of the forces as they're moving through space. So that's sort of the end product here in terms of understanding, is that when something's moving, it has something in it that's going in a direction, and your opposing force is something that it can hit. Okay, so in a sense your electrons are moving inside of you, and if I explode something or I bring energy in to cancel, that's going to create energy in the opposite direction, all that's really going to happen is it's going to keep making these exchanges, and whatever side has more pressure on it is the side that's going to migrate. Okay, so the pressure is just going to migrate through this process of reflecting. So you can sort of understand when something's moving and I hit it, all right, what's really going to happen is there's going to be a reflection. This is going to go this way, right? And the force in here is going to go that way. And so that's pretty much a continuation of what was happening. Instead of the force being now in the electron, it's going to be in the element of the photon. So this force is going to continue, not by moving the electron, but by moving a force in this direction, and a piece of the stuff that would be called the electromagnetic radiation, a photon type piece of energy, is going to leave. So it was in the form of electron. Now this motion is in the form of a photon, and this motion has now been converted to pressure this way, And that means that anything other, like another electron is here, that means I've now moved this electron closer to this electron, and now the pressure between them is going to increase. So I'm increasing the pressure inside here, which means there's going to be another force in this direction. So it just regenerates the circumstance that existed previously. The previous circumstance was you had one bit going this way, and through this process, right, you're going to end up with one bit going this way again. And then you're going to end up with one bit going this way. So it's a circle, you know, and something always, the circle just keeps continuing because nothing ever accounts for the first motion. I mean, I push something into a circle, it goes completely around to zero again, but it still has the initial extra bit. You never got rid of that little extra bit, okay? So the cancellations are all cancellations, but you never got rid of the first impulse, and so the first impulse just keeps doing its thing over time, and it keeps initiating a new circle, 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 a new circle. In this case, it's probably more like it goes forward, then it stops, okay? It waits for the pressure, it goes forward again, then it stops, it waits for the rebound pressure from the other electron, then it goes forward again, and then it stops. And so that's how these things are moving through space, is through this process of this exchange. So when there's something explodes between two objects, and that's pretty much how you generate electricity, is just to cause extra, you know, pressure between things. So there's a thing here and a thing here, and I create an explosion here, an expansion. The energy, right, goes in both directions. So if this was inside the gun, okay, this is the bullet, all right, this is the chamber of the gun, the energy is going both ways, and both objects are going to get hit with a wave of pressure, okay, the expansion pressure, and it's going to be a finite amount of high pressure. So like a nuclear bomb or something, there's places where it's really high pressure, and then it goes lower and lower and lower, you know, and decreases from there, and both surfaces are going to get hit with that pressure. And, you know, and now it's just a matter of whether the object is movable or immovable. So if the atoms in here can't be moved together, that is, they can't acquire all of them, you can't transfer the momentum between them really easy and they all move together, like if this is spongy material, well then you can understand if it's spongy, like the atoms aren't attached very strongly, then the atoms just fly apart, you know, and the chamber explodes. But if they're nice and rigid, like steel, and they're stuck to each other very, very securely, then it's an all or nothing thing. If they all don't move, then what they'll do is create vibrations, sound waves, inside the metal, and the metal will vibrate, and it'll resonate, and that's heat, okay? And it'll produce, you know, energy to the environment, it'll do lots of things, but some of it might even rebound, it might even reflect, okay? So now you're going to start, you know, the energy will go through the metal, it can't get out because there's not enough energy coming in, it's moving faster than the energy coming in, so reflections don't mean much, can't get out, so it bounces back into the other surface. So it's like it's trapped in there, and that's the ring of it, the vibration of it. And so it throws it back in this direction. The catch is that this all takes time, and by the time this pressure reflects, this bullet is already on its way. So it's already expanding the space in here, which means there's more distance for it to travel to get back to the bullet. So it's not likely to be able to do much in terms of add extra pressure. So the truth is, if I put a bigger object, a heavier object inside the gun, all right, there will be a little bit of a difference in the sense that the slow bullet gives me more chance to take a piece of the reflection that went this way and bounce it back to this way. And so now the pressure can get to the bullet, but it's probably a very slight amount technically, because it takes too much time really. The velocity of the bullet gets too fast for this distance to be able to get a reflection all the way back to the bullet again, to push the bullet. And the bullet's also reflecting some of the energy, so, you know. But the truth is, that's where the half kind of comes from. Is the idea is that when you do the explosion, the hard pressure has to hit both surfaces. Both are going to be affected by it. And it's either going to create a lot of heat, like the atoms will do a lot of jiggling, so they get very, very hot. And it's also going to create the fact that your whole gun might move. So unless you secure it against some other bigger, heavier mass, the gun starts moving just like the bullet, you know, in the sense that it goes much slower velocity because it's much more massive than the bullet. But the more you equalize that ratio, the lighter you make the gun, you know, the faster it wants to go from the pressure. And so it gets, you know, more and more necessary that you secure the gun, because the recoil is going to be even a higher velocity. So the heavier the gun in proportion to your bullet, the more stable the whole process is. But whatever, I'm not a ballistics expert, so I'm not the physics, I'm just saying, basically says these things. So anyway, so I'm just saying, so you can understand why a half is interesting, but frankly, nobody figures it that way. You don't sit there and say how much of the power of the gunpowder, the absolute power, is lost in the process. You just say how much gunpowder is usually going to produce so much momentum in a bullet. And that's basically how we define the energy of the gunpowder. Isn't in adding up both the actions. We're usually just measuring one of the actions. And so, you know, because we're not following the momentum in both directions. We're just following the momentum that's interesting. All right, but the real energy is, I mean, the half isn't, it isn't incorrect. It's just incorrect to apply it to the bullet and say the energy is now somehow twice as much energy because I understand that half the energy went a different direction. Well, you can't apply that direction to this object because it won't have anything to do with this object. Yeah. So if you were to make an absolute statement about momentum, that's where the F equals ma comes in handy. Okay, it's because what the A is adding is the half, because the accelerations are usually at half the rate, and that's because half the energy was used in creating acceleration in the opposite direction. So the half kind of gives you the idea that the actual force is twice as much as what you're going to get out of just mass and velocity, because the accelerating process really accelerated in both directions. Yeah, that's one way of saying it anyway. Alright, so do I need to, what else would be valuable here? So the point is that whether it's an electron moving, okay, or a proton, or whether it's the whole atom that moves, you have to understand that the movement is just a bias. That it means it has more pieces inside of it doing one thing, you know, going in a direction. Alright, continuing. Alright, so the idea is the universe has things of energy in it, and you got the littlest tiny bits, or what we're going to just say. Like I said, I don't want to have this argument about ether, pefer, whatever. There's little bits in the universe, okay, the smallest grains of universe, and they have a momentum and a direction, in my opinion. That's how it works. That makes sense. And they're what's creating photons, okay? You put 3 or 4 of them together, and that makes a pattern, and that pattern creates a form of energy that can do certain things, because it's like the tipping point argument. It can do things to electrons. You hit the electron once, doesn't do anything. You hit it, but if you hit it twice, when it's moving the wrong way, when it's going this way, and you add energy, you hit the energy when it's going back again, that's not going to do any good. On the cameras up here, right? So the whole tipping thing. To tip it, you got to hit it when it's going the same direction. You're throwing the energy in a second time while it's still moving the right way, so it can swing back, and hit it again, then you can tip it over. And that's the principle of electricity and what causes it. And so photons have a pattern, a frequency, and that's the tipping point frequency for the electrons. So, but the momentum starts there, okay? Then electrons can have momentum, movement, because they collect force. And then the atom itself has the pieces of the atom, the nucleus. And the nucleus is the key to perpetual motion. That is, the idea of matter keeps moving when you throw it somewhere. It's because it's really inside the nucleus that's happening. But anyway, so the atom itself can have a vector. And it's just everything has these vectors, and the vectors go a little deeper than just big fat atoms. And space itself is full of an atmosphere of energy, force. And when you block the force with a big earth or something, there's less force getting out because the force gets slowed down pushing matter. So when this force going the speed of light hits an electron, it's not going the speed of light anymore. You know, it has to push the electron. And that little sacrifice of energy is what's creating gravity. That's why every material object that has these electrons in it, it creates gravity. It's because it's the fact is the movement of the electrons is consuming some of the energy of the force that went in. So more stuff goes in that can come back out again. And that's a real loss to the universe. So although energy is always conserved, these will be things we'll say, I'll even say it, in a sense it's not always conserved, because when it's pushing an electron, the fact is it's not going the speed of light anymore, and going slower means you're not have the same energy. You have to have less energy because you are now pushing something, and as soon as it's not pushing, it goes back to its normal I'm free state. But anyway, so yeah, you don't have to believe all that stuff. I'm just saying I'll tell you it does make sense, but anyway, it does work as a way of understanding it. But yeah, so if you just get the vague idea that there's already energy in the universe, okay, it's already there. So there's no such thing as saying I was in empty space. I went into space and was in a complete vacuum. Well, not even close. Okay, the tons and tons of energy, tons and tons of this invisible radiation is hitting you all the time. All this stuff moving the speed of light. Yeah, you can sometimes see the electrons hitting you, and you can sometimes see the atoms hitting you. So the bigger the stuff gets, the easier it is to see that you're getting hit by stuff, but you're already getting hit by the universe, the energy in the universe. And if you kind of understand that it's just exchanges. So everything's an exchange. So the train creating heat on its wheels or some other thing, it's just another way of thinking of an exchange. It's not really a loss of energy, right? So if I create friction with a surface, I got a lumpy surface, and I roll something, I push something on the rough surface, and there's all kinds of atoms getting abraded and knocked off, and electrons and ions and all kinds of stuff, and it's causing all kinds of vibrations in this, and it's causing vibrations in this. Those vibrations are just energy vectors going in all kinds of directions, and it all ends up getting randomized and ends up going in all kinds of directions. Because in the universe there really is two choices. When energy hits electrons and protons, it can either push them in the direction it's going, or the energy can be diverted. And that's what makes heat possible, is the energy gets diverted for free. It gets changed in its direction. And by changing its direction, that's a pretty radical thing. So energy goes in this way, two hunks of clay swung into each other. Energy is coming in this way, momentum, and it's going to go out in this way and that way and that way and that way. It's going to be converted into a bunch of randomized directions of little bits moving in all kinds of directions. So you're just going to convert all the arrows going this way and this way into arrows going this way and that way and all kinds of other different directions. Because you're going to transfer the energy from photonic energy to electron energy to atomic energy to movement. So when I say energy, it's just movement. I change the movement from the littlest bits to the medium-sized bits to the little bigger bits to the bigger bits, and then to the whole frickin' object which I cause to move. And it's always the same thing. It's just a bias in a direction. It's just that there's more little bits of energy going one way than is going another way, and that's all it is. You have energy going inside of you going in every direction, but when I move something, it now has a little bit more going that way. Let's see if there's anything else to add to that. So there is no empty space, there is no pure vacuum, it's just a material vacuum. So that should be probably the way to say it. You can be in a material vacuum, but you can't be in an absolute vacuum. Energy is everywhere, and energy, like I said, it's just transfers. All you're doing is making the momentum, the bias, it goes somewhere, and you just follow it. The heat goes this way, and then it hits a cloud, and it goes that way, and then it comes down as rain, and then it goes over this way, and it goes. It just keep following the little bits of energy, but that's all you're doing. You're just following it. So it's coming into the universe in all these directions, and in our little entropy place here in the universe, we're just converting, and deflecting it. So we end up taking stuff going this way, and we end up making it all go that way in a laser beam or something. We're just changing, we're just tunneling, funneling, collecting energy going in all these directions, and we funnel it all in this one direction, and we just create pathways for energy based on the fact that electrons and protons are in patterns, and those patterns allow us to shoot all the energy that way, or the pattern allows you, the crystal, the this, the that. It's just a way of collecting, having collectors, and then having emitters that are different than the collector. The collector is really big, and then the emitter is really small, so we can channel and funnel and transfer energy into different directions. I'm just saying all the material objects. So all the big matter can have arrangements of matter, like the water molecule, that allow the energy to travel in directions and patterns, and every little crystal of metal has a different, orientation because of the arrangement of the electrons and the protons, and those crystals will pile up and they'll create another shape that's capable of moving energy in directions, blah, 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 blah. That's probably enough for this lesson. Yeah, so their theory, their model is not accurate. It's just, the standard model is just mush. And if you think in terms of just follow the energy, you'll get it. And another part of that is the Bohr model. This has got very... Anyway, of electrons circling and all this kind of stuff. There's likely not all that kind of energy in the atomic structure. It's more about electrons just vibrating because they're in pressure with each other, and they're pushing on each other constantly, and every one that gets hit with one little extra bit of force, that little bit of force makes them move closer to each other. They reflect energy back and forth, blah blah blah, and it's just a bunch of little bits trying to find arrangements there they can't be knocked out of. So atoms essentially create arrangements that you have to hit with an awful lot of energy to break. The attraction to the nucleus and the repulsion between each other is so perfect in these 100 elements that we know of that you really have to hit it hard. You have to throw a lot of energy in one place to break it from its structure. Well, anyway, then you're into chemistry and all the other subjects and blah 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 blah. The elemental function is simple. It is just movement, transferred from little things to big things, and then back into little things, and that's all it is. Nothing else going on here, and it's all about their momentum. The little things have very little momentum. The bigger the thing is you can move, and the faster you can make it move, the more energy it represents. Yeah, that really should be enough for now. Alright, so this has been a DraftScience video presentation. Thank you for your attention. I suppose I should say that now and then, but yeah, because it's nothing to thank any of you for. The complete lack of, tiny bit of support versus all the ridicule and harassment. Yeah, amazing. Yeah. I should just F-bomb you at every opportunity. Bastards.